Good afternoon, morning, or whatever time it is you watch this thing. This is a BIOL3465 Tropical Forest Ecology and Use lecture, and in this lecture I'm taking a look at tropical forests and global climate change. There is a fairly good section in the textbook by Gazul and Shiel, which I suggest you read. I will make sure that I put Gazul and Shiel, which is the textbook available in the bookshop, up on the reading list. So that's Tropical Rainforest Ecology, Diversity and Conservation. Alright, so this lecture I'm going to go through global climate change which is happening now, and I guess it's a natural extension from talking about how rainforest distributions have changed in the past. So, first of all, global climate change. What is global climate change? It's generally accepted that global climate is changing. Why is it changing? It is changing because there is a build-up of CO2 in the atmosphere, and all that CO2 is creating or holding more heat in the atmosphere than has previously been the case in human history. With all this heat held in the atmosphere, it means that the global average temperatures have been increasing. Now, this was first detected back in the 1960s at Mauna Loa Research Station in Hawaii, where they've been monitoring atmospheric CO2, and scientists there noticed that CO2 in the atmosphere was going up. There is seasonal fluctuations in carbon dioxide, as during the summer in the northern hemisphere carbon dioxide is actually drawn down, and you can see it drawn down during the course of the year over the summer, and that is because all those temperate forests are photosynthesizing and sucking all the carbon dioxide out of the air. Carbon dioxide rebounds during winter, the northern hemisphere winter, as all those temperate forests drop all their leaves and are just respiring and become carbon dioxide sources. Now, even though the carbon dioxide level in the atmosphere were going up and down on a seasonal basis during the course of the year, the average carbon dioxide amount in the atmosphere averaged over the seasonal basis was trending upwards, and it was a fairly consistent change. Okay, nobody thought much of this until certain atmospheric scientists noticed that there was an increase in temperature, an average increase in temperature. Actually, I think they saw this rising CO2 and they thought to themselves, what is this going to mean for the world? And one of the things which they hypothesized was that it's probably going to mean an increase in temperature. Okay, so why did atmospheric scientists immediately think of higher CO2, increase in atmospheric temperature? The reason was that in the geological past, in the geological history, there have been periods where CO2 has been higher in the atmosphere, and they have consistently been warmer than current temperatures. And if you remember back to the last lecture on tropical forest change through history, one of the hypotheses that explained the extinctions in the Devonian period of the first vascular land plants was that they were too efficient, and they basically sucked all the CO2 out of the atmosphere and created a ice age down there in the Devonian, and that devastated all those forests which were used to much more warm and wet, more tropical type conditions. The idea is that maybe even the ice ages during the Tertiary and the Quaternary, the cooling during the Tertiary and the ice ages during the Quaternary, were actually the result of all these tropical forests sucking all the carbon dioxide out of the air and reducing the greenhouse effect. And maybe with the increase in CO2 in the atmosphere, we are going to return to more warm and wet climate. So, it was noticed that the CO2 levels were going up, and it is noticed also now that the temperatures, the average global temperatures, are also increasing. So, what does this mean? Okay, well, first of all, why is the CO2 going up? I think you all know that. It's thought to be because of human activities. Humans are burning fossil fuels, which represent carbon, which has been sequestered away from the atmosphere underground. When you dig it up and you burn it, it's going to return CO2 to the atmosphere. It's just logical, although some people would tend to deny that. So, the burning of all these fossil fuels introduces carbon into the atmosphere in the form of carbon dioxide, which is a good greenhouse gas, and allows the atmosphere to hold more heat and therefore raises the average global temperature. So what influence is this going to have on the ecosystems around the world? Well, the rate of change in geological terms is very rapid. There is thought to have been a 1 degree Celsius increase in average global temperature already. And there is evidence that ecosystems around the world are already responding to the change. Okay, so how are tropical forests likely to be affected? And that's going to be the subject of this lecture. First of all, to understand how tropical forests are going to be affected, we need to know how the climate is going to change. Okay, we know that temperature is going to go up, and that's probably one of the most predictable things that we can model, because we know the rates at which carbon dioxide are going into the atmosphere, and we can estimate what sort of average temperature you're going to get in the atmosphere with a certain concentration of carbon. But climate is more than just temperature. Okay, as we saw in previous lectures, in the tropics temperature is relatively constant, and it's things like rainfall which really influence the distributions of biomes in the tropics. So how are we going to predict how global climate is going to change? Well, what scientists have done is tried to model the changes in the different climate parameters, such as heat distributions in the atmosphere and the hydrosphere, cloudiness, wind patterns, precipitation patterns, ocean currents. All of these things, both in the atmosphere and the hydrosphere, are going to influence the climate in different parts of the world. And in different parts of the world, changes are going to be different. So, for example, most of the models and the current temperature changes appear to be impacting in the temperate regions more than in the tropical regions. Okay, so temperatures have risen more, the average temperatures have risen more in the temperate regions of the Earth rather than in the tropical regions of the Earth. So in the temperate regions, winters are becoming milder and summers are becoming more hot. Okay, there has been some temperature increases in the the tropics, but they haven't been as much as the temperate regions. In terms of rainfall, rainfall is going to change, and it's not as clear how it will change because there are so many different factors influencing rainfall distributions around the world. Okay, patterns of convectional rainfall are probably better modeled and better understood because it's a straight heat balance equation. However, wind patterns and inevitable ocean current changes really do have a big impact on even convectional rainfall, but also orographic rainfall brought with wind. So for an example of that, an ocean current can affect your convectional rainfall if, for instance, an area of the ocean which is usually quite warm, convectional rainfall is going to come off that part of the ocean very efficiently, okay, because it doesn't need to heat up as much. But if now that part of the ocean is influenced by a cold current which is temporarily pushed off its course by some reason, like changes in wind patterns, for instance, it is going to mean that convectional rainfall just simply doesn't occur in that area for that particular time of year. Okay, so there are many different parameters which all feed into rainfall and precipitation distribution in the tropics. And you must take into account all of those things if you are going to try and model how rainfall distributions are going to change over time. Okay? So in the tropics, it's rainfall distribution, and by the opposite, the corollary, drought distributions, which really influence the patterns of different ecosystem types in the tropics. And rainfall distributions and precipitation distributions are the things which are some of the most difficult to predict. Okay? These global circulation models try and pull all of these different hydrospheric and atmospheric, all these different fluid dynamic models together to try and give a prediction on how global climate change will occur over the next 50 and the next 100 years. They're all predictive models, and the very nature of predictive models is they are never 100% accurate, and in particular with models, if you leave out parameters which are important, they are going to be way off. Okay? So these models are always going to be inherently suspect until they're proven correct. And that's just the nature of predictive models. Currently, the global circulation models are corrected and improved, and different parameters are given different weightings in different parts, and different parameters are included to try and understand how the dynamics of the situation will change. And the models are then tested against historical rainfall and temperature data, okay, and tinkered with to try and better match the models to the historical data. Okay, so to test the models, the scientists would use data from the last 20 years or so, and they would put their model to start 20 years ago, and they will let it run, and they will see how closely those models predicted the weather patterns for the past 20 years or so. Okay, so these models have become better and better at predicting the climate the rainfall distributions, the temperature changes over the last 20 years. Okay? Scientists are always working to try and improve these models. One research proposal that I've been involved with putting together from an American university is trying to look at how nitrogen impacts on global climate change and basically the carbon balance of the atmosphere. Nitrogen is thought to be limiting, at least in some tropical forest ecosystems, and if nitrogen is increased, as may happen with increases in CO2, meaning nitrogen fixing plants may be promoted, and thus increase the nitrogen in the ecosystem, that would increase the CO2 uptake of the forest. And if that effect is felt across all tropical forests, that can lead to a much higher absorption rate or sequestering of carbon from the atmosphere than is currently predicted. Okay, so little wrinkles, little parameters which have not been considered previously may have big impacts on the changes which will occur in the future with global climate change. So what is predicted by these global climate models in the Caribbean? It is predicted that temperatures will increase by 2 to 6 degrees within the next 50 to 100 years. And records show that temperatures regionally have already increased by about 1 degree Celsius. It's thought that rainfall will increase in some areas and decrease in others, and the latest I've seen is that Central American rainfall is predicted to decrease. Amazon basin rainfall, it's difficult to tell, and there really is not much consensus on how rainfall will change in the islands of the Antilles. One thing which scientists are predicting with some degree of confidence is that dry seasons will become more intense, so there'll be less dry season rain, at least in marginal or more seasonal climates, and wet seasons are likely to become wetter. Okay, so it's predicted that in seasonal environments the seasons will become more stark. Okay, I have not seen anything for Trinidad specifically. Whether or not convectional rainfall will occur around Trinidad for a greater period of time, what influence the changes in temperature is going to have on ocean currents. This is important because ocean currents at the moment bring quite warm water from the equator into the Caribbean and out up along the east coast of the United States and so on up to Iceland and northern Europe, and this current is known as the Gulf Stream. If, as predicted in some models, changes in salinity which drive this Gulf Stream occur, it is likely that that Gulf Stream will shut down, which will mean that there will be less warm water brought into the Caribbean, and that's going to have a big impact on the amount of rainfall that you're going to get in the Caribbean. Okay, that's just one prediction, one model which has been proposed. Other people have said that some parts of the Caribbean are likely to get more rainfall. One thing which is likely to happen is sea levels are going to rise. Now, sea level rises are caused by two factors. The first one that you probably heard about is these ice caps or big blocks of ice which project above the surface of the ocean. These blocks of ice are in places like Greenland, perched on top of the land, and in Antarctica, perched up on top of the land and therefore away from the oceans. Once those ice caps melt, all of the water, and that's millions and millions of cubic meters of water, will make its way into the oceans and so increase the sea levels of the oceans. So that's one way in which the sea levels will rise. Another way in which the sea levels will rise is simple thermal expansion. So when you heat up any sort of matter, it usually increases in size, increases in volume, And water is no different. If you heat up water, it will increase in volume. So if the average global temperature increases, and therefore the average temperature of the oceans increase, it will mean that the oceans will expand in volume, and so sea levels will rise. So sea levels are thought to increase by up to 1 meter in the Caribbean. The latest International Governmental Panel on Climate Change I saw predicted that rises of 85 centimeters are likely in many places around the world. So that's pretty close to that 1 meter rise. Now 1 meter doesn't sound that much, but when you consider that many of the cities of the world were founded on the basis of being ports for shipping, and are therefore situated right on the coastlines, and any sort of sea level rise is going to lead to flooding, including in Port of Spain. So Port of Spain is likely to be flooded more and more frequently as sea level begins to rise. It's also going to have a big impact on coastal ecosystems. A very important coastal ecosystem are mangroves. Okay, and I'll talk more about how coastal ecosystems, and in particular mangroves, are going to be affected. Hurricanes are thought to going to be increase in frequency and severity. Now, the reason why we have hurricanes is because of extreme energy in the atmosphere. With increasing temperature, there's going to be more energy in the atmosphere. Is this going to lead to more hurricanes? Probably. Whether or not the distribution of these hurricanes, or where they occur, is going to happen is of critical importance to Trinidad and Tobago, because at the moment we are just outside of the hurricane belt. So hurricanes, when they are generated in the Atlantic, in the equatorial regions, tend to deflect northwards as they run to the west, and therefore they don't usually hit Trinidad, and only occasionally will they pass close to or over Tobago. So if hurricanes were to shift their distribution and maybe form and track much further south, then they are likely to have a big impact on ecosystems and human endeavor in Trinidad and also Tobago. Okay. Another important factor which people don't usually talk about is the cloud base. Now, the cloud base is the altitude at which orographic rainfall or clouds formed by orographic effects forms. Now, this is usually fairly consistent because the wind coming off the ocean, which is forced upwards, is usually of a consistent humidity and a consistent temperature, and therefore when it gets to an altitude, it starts to form clouds. The precipitation occurs and droplets are formed and clouds are formed. Now, if temperature in the atmosphere is generally higher, now that means that cloud bases, the condensation is likely to occur at colder temperatures, the temperatures required for condensation are likely to occur at much higher altitudes now. Okay, because the general temperature is warmer. So that means that cloud bases are likely to rise in altitude. And this is going to have important implications for ecosystems which rely on the formation of that cloud and also rely on orographic rainfall. So cloud forest ecosystems are likely to be heavily impacted, and those which are concentrated at the tops of the mountains, like for instance in Trinidad, there's only a couple of places in Trinidad, maybe the top of Mont Blanc, the top of Serra del Aripo, and the top of El Tacuch, which have cloud based ecosystems which rely on a lot of cloud forming to give them more give them more precipitation through condensation, but also to cut light so vegetation can't grow too tall and outcompete things. If the cloud base rises, most of those ecosystems will collapse and change. So what do you think? Well, many of the endemic plants in Trinidad are actually found in these cloud forests. Okay, but anyway, let's talk more generally. Tropical biomes. Just a reminder of the physical parameters of many of the different tropical biomes around the world. Tropical rainforests generally have a rainfall of above 1800 millimeters per annum. They have a low seasonality of rainfall. The rainfall is distributed throughout the year. A warm temperature. Temperature never gets below about 18 degrees Celsius, even in the depths of winter at night. And there tends to be very high biodiversity. Tropical deciduous forests tend to have 1300 to 2400 millimeters of rainfall per annum. So they overlap tropical rainforests, but the reason why they're deciduous forests is because they have 4 or more months of the year where rainfall is below 50 millimeters. So they have a high seasonality of rainfall. Temperature is much the same, and because of this seasonality of rainfall, they have moderately high biodiversity. And if you remember, some of the models predict that seasonality of rainfall is going to increase in many parts of the tropics and the Caribbean. Tropical savannas are similar to tropical dry forests, or overlap heavily with tropical dry forests, but they will tend to have less rainfall. They will also have a very high seasonality of rainfalls. Temperatures, again, at about or above 18 degrees Celsius, very similar there, and they have moderate to low biodiversity. Okay, the high seasonality of rainfall promotes burning and fires in many areas, and that's why we'd have savannas and not tropical dry forests. Tropical deserts occur in areas where there is less than 400 millimeters of rainfall per year. The rainfall is erratic, doesn't even get to be seasonal. You get a fall every now and again, but it's not predictable. The biodiversity is low because living things can't really cope with this type of rainfall. Temperature, well, not many living things. Temperature again is the same because temperature is constant across the tropics. So the main changes with global climate change will be changes, well, in the tropics anyway, will be changes in rainfall. So global climate change will mean changes in rainfall, amount and seasonality in a given area. That means that tropical rainforest biodiversity will quite often be accompanied by changes from one tropical biome to another. Okay? So some species will be able to cope with the changes in rainfall amount and seasonality, whether that rainfall be increased in amount or increased in seasonality, or decreased in amount and decreased in seasonality. Some species will be favored and some will be penalized or become less able to cope, less productive, and they will change to another species. Okay, so I've got two seedlings of tropical trees here, one of which may replace the other as things get drier. Okay, changes in tropical forest biodiversity excuse me, will change by these changes from one tropical biome to the other. So for instance, if we get increases in seasonality of the rainfall, which leads to a tropical rainforest, increasing the proportion of deciduous trees in its canopy, and therefore changes to a tropical deciduous forest, biodiversity is likely to fall as some of the more wetter adapted species drop out of the ecosystem because they simply don't have enough moisture during the dry season. So you'll see that as some trees, the trees which cannot drop their leaves, basically they will just keep on photosynthesizing into the dry season, keep on losing water through transpiration until they basically die. Okay? Other trees can close their stomata, but when the stomata are closed, they retain their leaves. The stomata are closed. They're still respiring with those leaves. It's a huge respiration load, and it means that the carbon balance is not kept in that individual or within that species. And when the carbon balance goes into the negative, means the tree cannot grow, it cannot replace damaged leaves, damaged organisms, and so it gradually begins to die because it cannot retain a positive carbon balance. Okay? Species compositions then will change within these biomes. Okay, as on the tree side of things, evergreen trees will give way in deciduous biomes, and if seasonality decreases as amount increases, then evergreen trees will begin to replace the deciduous trees. Okay? Because we cannot accurately predict how the rainfall changes will occur because of all the complicated interactions, abiotic interactions, not all tropical areas will be affected by rainfall change equally. Looking at Trinidad, Trinidad is right on the east coast of a continent. It tends to benefit from rainfall in the dry season, which is gathered together by the trade winds and deposited on the east coast of Trinidad. So we tend to have tropical rainforests over much of Trinidad, and we only get into the deciduous forest in the westernmost parts of the northern range, where rain shadow effects mean that the rainfall seasonality is very high down the islands and in the northwest peninsula. What will change? Nobody is too sure, but it could be, one scenario is that with the increased temperatures, convectional rainfall will visit Trinidad for longer periods of time, longer periods of the year, so the seasonality of the rainfall will actually decrease, and therefore rainforest species, evergreen rainforest species, will gain the ascendancies and begin to invade the more deciduous areas. Okay? So in the case of Trinidad, it could be that we get a higher annual rainfall and a lower seasonality of rainfall, and therefore species which favor these types of environments begin to expand through much of Trinidad at the expense of species which can cope with a more seasonal climate through doing things like deciduous dropping their leaves. So some species of trees in Trinidad which favor the high amounts of rainfall are things like Carapa guianensis, the crapo tree, and Mora excelsa, the mora tree. Both of these favor wetter environments, so they may actually be favored by global climate change and be able to expand across the island. On the other hand, species like maybe cedar, which favors a more seasonal environment and is able to drop its leaves, or black pui, which is one of those flowering pui species which tend to favor more seasonal, drier areas and also drop their leaves and flower during the dry season. They may actually be disadvantaged by the decreased seasonality, in that they will drop their leaves when they don't need to, and the evergreen trees will be able to ride over the top of them with their increased productivity. So with a biome change from rainforest to deciduous forest, there will be an increase in deciduous species and a decrease in evergreen species. So as the rainfall becomes more seasonal, you would tend to get more deciduous species. Okay. However, all of the evergreen species will not be lost from the landscape. If you remember from the last lecture, there will be what is known as local refugia in the landscape, and in particular along watercourses where water is concentrated in the landscape. You will probably be able to get soil water which lasts throughout the dry season, and so evergreen species will be able to survive along these watercourses. In places where deciduous forest currently exists, maybe less so in Trinidad, but there's probably good examples in Trinidad. If you look up in the slopes of the northern range behind places like Mount St. Benedict, Tunapuna, Aruca, and places going west, deciduous forest exists in those environments where there is a bit of a rain shadow effect because of the northern range, up to about Arima, and those forests tend to have a high proportion of deciduous species and species which can cope with lower rainfall during the dry season. There may be more intense dry seasons, and if all things being equal, the species will probably retain their forest nature, and maybe there'll be more deciduous species, but it would remain a forest. But a big difference, and particularly in those areas which are the most populated parts of Trinidad, the east-west corridor runs from Port of Spain to Arima. There's a lot of people there, and people, as you know, mean increases in ignition sources, and so fire will probably increase with the increase in dry season if seasonality increases in Trinidad. So the forests will be burnt on a regular basis, and you'll start to get the emergence of savanna type vegetation, which you get now on the hills behind Tunapuna. If you look out behind Tunapuna there are several hills which are just basically grass slopes. Now there are other slopes which were like that behind St. Joseph, and that was actually known as the St. Joseph Savanna. And the St. Joseph Savanna exists where we now have those pine forests up on Mount St. Benedict. Okay, the reason why we had that St. Joseph Savanna was the same reason why we have the Tunapuna Savanna there. The Tunapuna fire savanna there is because fire burnt it every dry season. So with the increase in seasonality, there will be an increase in fire, and deciduous forests will convert to savanna forests. And this sort of thing will be mirrored around the world. Okay? So with increasing seasonality, humans will increase the amount of savanna over deciduous forest. Where there is an increase in seasonality, for instance, where it's predicted in Central America, parts of the Yucatan Peninsula, where there is now currently rainforest, and deciduous forest become more seasonal, going to become more prone to fire, and may actually convert to tropical savanna over time as they get repeatedly burnt. Okay? So that's rainfall changes with climate change. I want to talk a little bit more about some of the other effects of other parameters which are going to occur along with the rainfall changes and the higher temperature changes. And one of these effects, which is shown to be real, is carbon fertilization. Now, when you have higher CO2 levels in the atmosphere, it means that plant photosynthesis tends to be much more efficient. Okay? Higher CO2 levels means that CO2 will diffuse into the leaves much more readily and quicker. So the plant does not need to keep its stomata open for as long a period of time to get all the photosynthetic products it needs to maintain its respiration costs. Okay? So therefore, what is known as the efficiency, the water use efficiency of many plants will and has increased with the higher CO2 concentration in the atmosphere. So, all things being equal and assuming no change in rainfall, the biomass of a tropical rainforest should increase with carbon fertilization. Okay? So for plants or trees in the rainforest will simply be able to photosynthesize more efficiently and therefore be able to have more carbon sequestered and therefore increase their biomass. Okay? Some plant functional groups may be favored over others with carbon fertilization. C3 plants will tend to be favored over C4 plants. C3 plants have no particular mechanism for increasing CO2 concentration in their mesophils and making photosynthesis run faster. So they are going to be very responsive to increases in CO2 in the atmosphere. On the other hand, C4 plants, which include many of these grasses and other epiphytes and so on, have physiological mechanisms which concentrate CO2 and allow them to operate as if they're in a high CO2 environment already, and because of that they have high water use efficiency. These types of plants tend to be favored in drier or more seasonal environments. If carbon concentrations are higher, then C3 plants are not going to need these adaptations of the C4 plants, and so they are going to be favored because the C4 plants, all these concentration mechanisms require energy, they require physiological costs which the C3 plants don't have to bear. So C3 plants will be favored by carbon fertilization over C4 plants. Middle successional stage trees tend to be favored over understory trees. Okay? These middle successional stage trees will be able to utilize the light which they have access to fully capitalize on this carbon fertilization. The understory trees are already limited by light, so carbon fertilization isn't going to change that limiting factor for them. And in fact, the middle successional stage trees will increase their canopy and therefore deepen shade for the understory trees, so they may actually be knocked back. The understory trees, however, will be compensated by the fact that they need to keep their stomata open less, because they will be able to photosynthesize the same amount in a shorter period of time with the high CO2 levels. However, some of these understory trees have simply lost the ability to control water loss through stomatal closure, because they've had to keep their stomata open all the time. Okay? So, some functional groups will be favored by carbon fertilization over others. Okay? And in fact, medium long-term research in the Amazon basin in parts of forests which haven't been touched seem to show that the biomass of tropical forests are actually increasing, or have been increasing over the past 40 years or so. Nobody really knows why this biomass is increasing, because it's thought that the amount of CO2 fixed through photosynthesis in a mature tree is pretty much balanced by the amount of CO2 emitted by that tree in respiration costs. So if the tree is in carbon balance, then how will it increase biomass? And yet it has been found that biomass of these forests in long-term research plots have shown that the biomass has been increasing over the past 40 years. And one of the explanations invoked is this carbon fertilization. Okay? So it remains to be seen whether carbon fertilization is going to have a big impact on the amount of CO2 in the atmosphere, okay, and whether it will counterbalance any sort of runaway or rising CO2 and therefore temperatures around the world. Okay, there will be temperature rises, and this is going to have a subtle effect on living things. Now, we've talked about how temperature is going to rise and how that's going to throw off the circulation of moisture in the atmosphere and the hydrosphere, and so change temperature, and therefore that's going to have big impacts on the distributions of tropical biomes. But as temperature rises, it also has another very big effect on tropical biomes, in that respiration will increase. Generally, respiration shows an increase in levels as temperature increases, and it's a fairly linear increase. So you increase the temperature by a certain amount, and respiration will go up by a certain amount. The reason for this is because the enzymes which conduct respiration operate more efficiently and therefore at an optimal rate, so respiration will increase and the animals will be able to do more. Things will break down more and so on. Okay? Because of this, respiration in these trees are likely to increase, and that may counteract any gains in biomass which occur due to CO2 fertilization. Okay, so even though these trees are gaining biomass, it may be that in the future, as the temperature rises, respiration costs increase, and therefore this biomass will then be lost, because these trees will have to use more of that the increased photosynthetic capacity to pay the respiration costs. Okay, and another very important area where temperature rises and respiration increases will increase the amount of CO2 which comes out of a tropical rainforest ecosystem, is that dead organic matter in the soil will begin to be converted or eaten up, and the organisms which do the breakdown will operate more efficiently, and therefore the carbon in the atmosphere will increase as CO2 respiration, CO2 from respiration, from tropical rainforests, from soil increases. Okay? So, tropical rainforests, as temperature rises through respiration, may actually become a source of carbon, because quite often there is a fair amount of stores of carbon in the soil as humus and undecomposed organic material. If more of that humus and more of that undecomposed organic material is lost through respiration, there is going to be more CO2 entering the atmosphere. And this is actually a very important effect which has scientists very worried, because the amount of carbon in the soil as humus and undecomposed dead organic matter is huge. Quite often it rivals the amount in the biomass. So any increase of release of CO2 from this pool is likely to have a big influence on the atmospheric carbon dioxide concentration. Eventually, however, the temperature rises will stabilize, and there will be a new balance between photosynthesis and respiration, which will eventually come about. Okay, so the increase in photosynthesis will be matched by the increase in respiration, and whatever biomass of the forest which results from that will become the new normal. Right, so biome migration. The efficiency of change from one biome to the next will be determined by the ability of species to migrate. This is most important in temperate regions, as cool adapted species must migrate northwards or southwards closer to the poles, okay, or they are likely to be overtaken by increased temperatures, and in some cases be outcompeted by species which can use the higher temperatures or the longer growing seasons more efficiently than these cold adapted species. But migration can also occur in the tropics, and in particular we're talking about migration from habitats which become drier into habitats which become wetter or maintain their rainfall. And this is usually over altitudinal ranges. So species which are more used to lowland conditions may need to migrate up to a higher altitude to find the climate which they have evolved for, but at a higher altitude. The biotic conditions will move up to a higher altitude, and the species will need to follow that. Now, this migration can be blocked by natural and human factors. If there isn't a continuous natural habitat which these plants and animals can cross, then they may not be able to migrate to parts of the landscape which allow them to survive. So if there are, say for instance, cleared areas preventing these lowland species migrating up the mountains, then these lowland species will become extinct. Okay? So low migration rates can mean biodiversity crashes, okay, as all the species suited to the new climate don't reach that new climate. Okay? So this may cause or may exacerbate the wave of biodiversity extinctions around the world which is occurring today. Okay, so as I was saying, with altitudinal changes Changes in temperature will affect adiabatic cooling. With altitude, life zones will shift up the mountains and species may have to follow them. As I mentioned earlier, cloud bases may rise or change, reducing mist precipitation and therefore reducing the range of montane cloud forests. High altitude endemics may be threatened with loss of habitat. So in Trinidad, for example, about 50% of the endemic plant species which are found in Trinidad are actually found on the tops of the mountains of the northern range, in places like Serra del Aripo, El Tecuch, Mont Bleu. And if the cloud base rises, their habitat will be lost and they really have nowhere to migrate to. So biodiversity may be severely affected with this change in climate and changes in altitudinal shifts of the climate zones. Okay, sea level rises. Sea level rising is rising at approximately 2 millimeters per year. It's already risen about half a meter in the Caribbean, and it's the coastal ecosystems which are most likely to be affected, as you may gather. Mangroves are likely to be eroded on the seaward side, and they need to colonize on the landward side. Now, all things being equal, they will probably maintain their extent, as quickly as they are lost on the seaward side, they would colonize the more flooded land on the landward side. It's only when these migration routes are blocked, as they would be, say for instance, behind the Caroni Swamp, where the Solomon Hocho Highway will block the migration of mangroves inland. So coastal ecosystems will be flooded, and if they cannot migrate inland, they may be killed off and reduced in extent. Coastal swamps also will suffer the same fate as mangroves, and hopefully they'll be able to migrate inland. Hurricanes, as I've said before, it's thought that hurricanes will increase in frequency and severity. More energy in the atmosphere through higher temperatures may mean more hurricanes. Forest structure may change, and maybe composition will change to species which are better able to cope with increased numbers of hurricanes. Sorry about the voices in the background. It's those bloody biochemists outside my office shooting off their big mouths once again. Effects of sea level rise will be increased by storm surges which are associated with hurricanes. So hurricanes not only are associated with high levels of winds, but also high levels of rainfall, and on coastal areas, storm surges, where mounds of water are pushed in front of the massive winds of a hurricane and can cause rapid stochastic swamping of coastal ecosystem. It's not known what will happen with hurricanes, whether they will migrate or increase their area that they affect closer to the equator. It's likely they will increase their frequency further north or closer to the poles, but will they go closer to the equator? We just don't know. Excuse me for a minute. Right, where was I? Forest structure and maybe composition will be changed. Effects of sea level rise will be increased by storm surges, and it is not known how those distributions of hurricanes will change. Hopefully they won't come any closer to Trinidad. Who knows? So what can we do? We can create protected areas that are large enough and connected enough to allow migration of species to new biomes along rainfall or altitudinal gradients. We can do that. So for instance, an example of that would be to establish a protected area from the lowlands right up to the tops of the ridges in the northern range, a continuous one, so that species in the lowlands will be able to migrate up those altitudes. There's only a few places in the Northern Range which we can do that now, because there's only a few places where the ecosystems have been protected all the way down from the highlands down to the lowlands. Matura is one area. The northern slopes of the Northern Range are better off than the southern slopes, and the further west you go, the more problematic it gets to find natural ecosystems which persist right from the ridge tops down into the lowlands. But we need to find them, and we need to protect them so they can preserve the species which may be affected by global climate change. We need to put more resources into preventing fire. So fire has got the potential to really radically change ecosystems in Trinidad. If they become more seasonal, then fire is probably going to be the agent which degrades and changes those ecosystems maybe into savanna ecosystems, reducing biodiversity and so on. So more resources like fire towers, fire bombers, having personnel who are able to claim overtime for fighting fires are all needed. We need to facilitate the migration of other ecosystems like mangroves from the coast and the coastal swamps. Okay, so the Solomon-Hochoi Highway must not be a barrier to the Caroni Swamp being able to migrate eastwards as the sea level rises. We need to monitor changes in montane ecosystem to try and see if these specialist high altitude species will be affected by changes to climate at the top of these mountains. Okay, so all of these things can be done to see whether we can mitigate the changes or the effects of global climate change on tropical forest. Hopefully you've got a pretty good idea of how global climate change will affect these forests now. Thank you very much. Bye bye.